The field that I was always very interested in and worked in for a few years is holography. And holography can be used to record a three-dimensional scene. Everybody's familiar with display holograms. You see them in a lot of different places. Even on the back of your credit card, you can see a hologram. And that three-dimensional, the ability to capture that three-dimensional information was first discovered by Dennis Gaber in 1948. 4 lasers were introduced. And this diagram here is from a very well-known paper by Leith and Upatniks, who were at the University of Michigan at the time, published in 1963. And this diagram figured in Dennis Gaber's Nobel lecture in 1971. It's a little bit indistinct, but basically this plane here is what he classes, or what Leith and Upatniks class is a photographic plate. In fact, photographic or holographic plate relies on the same chemistry as photographic, but it achieves it works at a much higher spatial resolution. The recording plane is here, and a laser beam comes in here, and as part of that laser beam illuminates the holographic plate. Part of the laser beam is deflected and is used to illuminate the object, and that object scatters light also towards the holographic plate. So the holographic plate has light both from the object and the unscattered light from the reference beam. These two beams interfere together. As you know, when you have if you project a laser beam on the wall, you get speckled because of constructive and destructive interference between light that's mutually coherent. And the same thing happens on a holographic plane. You get a set of fringes which basically encodes the complex information about the weight, the light front, as intensity distribution. You can record a very intricate fringe pattern on the holographic plate, and when developed and put back in the same location and illuminated with the original reference beam, you have a reconstruction of the original wavefront from the light scattered from the object. I mean, initial holograms were made of things like coins, fairly gross objects, but the same principle, the same basic principle can be used to record the location of particles, seed particles in a volume. The key thing about holography is that it can record submicron particles with a very large measurement depth. One of the things about this technique here, this photogrammetric technique, is that in order to see through the whole volume, you have to use a smaller aperture to increase the depth of field. That smaller aperture reduces the resolution of the system. As the aperture decreases, the point spread function, or the smallest resolvable object, gets greater. The key thing with holography is that you achieve both submicron resolution, and that you can resolve tiny little features, but you can also record a very large measurement depth, and it overcomes the classical imaging limitation of depth of focus with small f number. As I said, the complex light field from the object mixes with mutually coherent reference beam, given an interference pattern, which is your hologram. And the developed emulsion is illuminated to reconstruct the original wavefront. Just for your information, a very common film used for holography, 1056, has a resolution of 4,000 lines per millimeter. That's roughly equivalent to 0.125 micron pixel size, if you were to relate it to a digital sensor. And it has a dynamic range of greater than 5 orders of magnitude compared to 3-4 orders of even current CCD or CMOS cameras. The simplest setup for particle field holography, for doing PIV in a volume, is just to use inline holography. And that uses just an expanded laser beam, which comes through the measurement volume. And some of the light is scattered from the particles, and some of the light is not. And the light that's not scattered acts as the reference beam. The scattered light is obviously the object beam, and this produces a specklegram that looks roughly like that. And when re-illuminated, you can then reconstruct both a virtual and a real image of the particles. And this technique, this inline holography technique, has been utilized by a number of researchers. Principally, I guess, Huimen and Pasek Hussein worked a lot in the inline holography as a means of recording flow fields. And this is what they managed to achieve with this. They actually used a an inline recording system, but with off-axis viewing. One of the principal disadvantages of inline viewing is that you also have, you're looking straight into the laser beam, and you can visualize the particles, but they're in a very strong speckle background. So inline has the advantage of being simple, but the disadvantage that the signal-to-noise ratio is not so good. And the way in which the particles are reconstructed means that they don't have a lot, they're not well discriminated in the depth direction. So there's some significant disadvantages there. Off-axis holography applied to volumetric measurements was done in an amazing paper by Donald Barnhart and Ron Adrian. They address a number of key limitations in holography, both off-axis and inline, within one experiment. In off-axis holography, you have your reference beam coming in from the side, and it's physically separate from the object beam. The object beam coming down here illuminates the measurement volume here, and light scattered from the particles in the measurement volume is collected using this relay optic and then projected onto the film plate here. The reason they have this is because they want to use the near forward scattered light, which is much brighter and stronger. The disadvantage, though, is that they're using these optics, and these optics will aberrate the light field and cause distortions in the reconstructed field. So they did a very clever thing. They basically took the recording system, and when they developed their film, they replayed the hologram by illuminating the holographic plate from the back using the phase conjugate, or the reverse of the wave, as is illustrated here. And they replayed the distorted wavefront back through the same optics and recreated a nice, sharp, real image, meaning that you could actually put a screen against it and see the points of light. Yeah. They recreated a real reconstruction of the original measurement volume back in the same volume that it was occupied. So they're using, in addition to this, they're using multiplex off-axis arrangement. That means that you've got laser pulse 1 and laser pulse 2, both recorded onto the same holographic plate. Yeah. And at the time of reconstruction, you can switch on one by illuminating with the appropriate reference beam, switch that one off, and then switch on 2. So you can reconstruct the first and the second exposure separately. Scan with a CCD array the region that you want to look at, and then do cross-correlation later on to resolve the vector field. So this whole application involved a lot of optical hardware and at least a few very nice techniques combined to facilitate kind of volumetric measurements with good resolution and fairly large dynamic range. One limitation, though, that was difficult to overcome is that holographic plates and films suffer from emulsion shrinkage. But once you've recorded it and then you've gone to the darkroom and developed it and fixed it, it's subject to kind of shrinkage or distortion. And that will always be a limiting factor in measuring the displacement and the location of the particles. A third setup. The reason I give these three different setups is really just to illustrate the broad range of different possible configurations that can be used for holography, each of which might address one or other limitation that others have. In this setup, this was in the lab of Joe Katz, he used a hybrid inline off-axis system. So basically he's using, the advantages of inline is that you've got your laser beam going through the measurement volume and you're relying on the near forward scattered light. But it's hybrid in that it has also this reference beam as well. So one laser is taken and divided essentially into three. You've got beam splitters there to divide off some of the light. And that illuminates the